Right now, at this precise moment on October 27, 2025, an object the size of Manhattan is racing through our inner solar system at 221,000 kilometers per hour, and in precisely 48 hours, it will disappear behind the sun when no Earth-based telescope can observe it. That object reached perihelion yesterday, October 29, at 11:36 UTC, executing what astronomers call the Oberth maneuver window, the most fuel-efficient moment for any spacecraft to alter its trajectory. The timing is mathematically perfect, the location is geometrically impossible to observe from Earth, and the chemistry is wrong for a comet. 8 separate anomalies have been catalogued since discovery on July 1st, each defensible on its own, but stacked together, they form a pattern that violates our models of how interstellar objects should behave. Let that sink in. The Atlas Survey Telescope in Rio Hurtado, Chile, first detected object 3I/Atlas on July 1st, 2025, at a distance of 4.5 astronomical units from the Sunday. The designation 3I means third interstellar, the third confirmed object from beyond our solar system, after 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Within 72 hours of discovery, the Minor Planet Center had compiled 122 observations from 31 different observatories worldwide. Pre-discovery observations from the Zwicky Transient Facility extended the detection arc back to June 14th. The Transiting Exoplanet Survey Satellite, TESS, had captured images as early as May 7th, when the object was already active at 6.4 astronomical units, far beyond where water ice sublimation should begin. The Vera Rubin Observatory accidentally photographed it during commissioning tests between June 21st and July 3rd, 2 weeks before official discovery. Every major observational network had seen it. No one realized what they were looking at. Think of astronomical observation networks as a global early warning system. Each telescope, a lighthouse, sweeping its beam across the cosmic ocean. Each detection a flash of Morse code transmitted to the Minor Planet Center, where software triangulates position, velocity, and trajectory. That triangulation revealed a hyperbolic orbit, the signature of an unbound visitor passing through our system exactly once. The orbital eccentricity measured 1.003, meaning this object will never return. Its inclination to the ecliptic plane, the flat disk where planets orbit, measured 4.89 degrees. Pause on that number. The first interstellar object, Oumuamua, arrived at an inclination of 123 degrees. The second, Borisov, came in at 44 degrees. Both arrived from random directions in the galactic disk, exactly as theory predicts. 3I Atlas arrived almost perfectly aligned with the plane of planetary orbits, a geometric configuration with a random probability of 0.2%. The Hubble Space Telescope imaged 3I Atlas on July 21st, 2025, when the object was 446 million kilometers from Earth. The resolution achieved was unprecedented for an interstellar visitor, revealing a teardrop-shaped coma measuring approximately 26,400 kilometers by 24,700 kilometers, nearly twice Earth's diameter. The nucleus diameter was constrained to between 440 meters minimum and 5.6 kilometers maximum. Subsequent observations from ground-based facilities pushed the lower bound to 5 kilometers based on light curve analysis and lack of detectable non-gravitational acceleration, 5 kilometers. 1I Oumuamua measured roughly 400 meters across. 2I Borisov's nucleus was less than 1 kilometer. 3I Atlas is between 1,000 and 1 million times more massive than the previous interstellar visitors, yet it moves faster than both. At discovery, it was traveling at 61 kilometers per second. Current velocity exceeds 68 kilometers per second. The kinetic energy scales with mass times velocity squared. This object carries more momentum than anything interstellar we have ever detected. Here is the terrifying part. The James Webb Space Telescope pointed its near-infrared spectrograph at 3I Atlas on August 6, 2025. The spectral signature showed carbon dioxide, water, carbon monoxide, carbonyl sulfide, and water ice, standard cometary volatiles. The carbon dioxide to water ice ratio measured 8:1, among the highest ever recorded. Normal solar system comets show ratios near 1:1 or lower. Carbon dioxide sublimates at much greater distances from the Sun than water, which explains the early activity observed by TESS. The mass loss rate measured 150 kilograms per second at 3.32 astronomical units. Theory predicts that rate should scale with the inverse square of solar distance, accelerating exponentially as the object approaches perihelion. From July through October, 3I Atlas is estimated to have lost approximately 2 million tons of material, less than 0.005% of its total mass, equivalent to ablating a 4 centimeter surface layer from a 5-kilometer sphere. You cannot determine internal composition from analyzing exhaust plumes. We have sampled only the skin, but the chemistry was not the first problem. The morphology was wrong. Images from the Keck 2 telescope in Hawaii on August 23rd showed emission of cyanide and nickel, typical cometary species, but the emissions were not confined to the antisolar direction. A jet of material pointed directly toward the Sun, not away from it. This so-called anti-tail measured 10 times longer than it was wide, a narrow beam of scattered sunlight, contradicting every geometric model of radiation pressure and solar wind. Comet tails point away from the Sun because photons and charged particles push dust and ions in the antisolar direction. Jets can point sunward during active outgassing, but they are small, diffuse, typically less than 1/10 the scale of the main coma. The structure imaged on 3I Atlas was coherent, persistent, dominant. Observations from the Gemini South Observatory, the Nordic Optical Telescope, and the 2-meter twin telescope at Tidey Observatory in the Canary Islands confirmed the feature throughout August. By early September, the anti-tail began to fade, and a conventional tail developed exactly as models of carbon dioxide-driven sublimation predict when the flux transitions from ice grains to refractory dust at closer solar distances. The transition was normal. The initial sunward jet was not. Let me be explicit about what we can and cannot conclude. Sunward jets are known in cometary science. They occur when localized outgassing on the day side of a rotating nucleus ejects material before rotation carries it into shadow. The persistence and coherence of the 3I Atlas feature suggest either a fixed active region continuously illuminated or a non-rotating or very slowly rotating body. The lack of detectable light curve variation supports slow or zero rotation. Most comets spin with periods of hours to days. A 5-kilometer object with negligible rotation is mechanically unusual but not physically prohibited. Tidal locking or collisional damping in a dense birth environment could produce such a state. A slowly rotating comet with high carbon dioxide content and localized active vents could, in principle, produce the observed morphology. That is the conservative interpretation. It requires no new physics. It is also statistically uncomfortable. Stack the anomalies. 1. Trajectory aligned to within 5 degrees of the ecliptic with probability 0.2% for random orientation. 2. Nucleus mass 1,000 to 1 million times greater than previous interstellar objects while moving faster. 3. Arrival timing permits close flybys of Mars, Venus, and Jupiter while remaining unobservable from Earth at perihelion. 4. Carbon dioxide to water ratio of 8:1, extreme for any comet. 5. Early activity at 6.4 astronomical units driven by volatile ices other than water. 6. Persistent sunward jet observed for 2 months. 7. Negligible rotation rate inferred from lack of brightness variation. 8. Dimmer than predicted brightness based on coma size and distance, suggesting either unexpected albedo or geometry effects. Each anomaly has a mundane explanation. Each can be rationalized individually. Together, they form what risk analysts call a compounding improbability. Assign each anomaly a 10% chance of occurring naturally. The joint probability of all 8 occurring simultaneously in one object is 10 to the negative 8, 1 in 100 million. That calculation is illustrative, not rigorous. The actual probabilities are correlated and unknown, but the principle holds. Extraordinary claims require extraordinary evidence. An absence of evidence is not evidence of absence, but accumulation of anomalies shifts the burden of proof. We do not have evidence of artificiality. We have an absence of satisfying natural explanations for the ensemble of observations. Protocols exist for this situation. The International Asteroid Warning Network, IAWN, coordinates planetary defense activities among space agencies globally. On October 21st, NASA issued a technical alert designating 3I Atlas as a Category 2 observation priority under the Minor Planet Center Bulletin MPEC 2025 U142. The alert did not invoke defense measures. It activated enhanced monitoring protocols and scheduled a training exercise for November 27th through January 27th, 2026, simulating detection and tracking of an object with hyperbolic trajectory and unpredictable activity. The exercise is procedural. The timing is coincidental. The wording is careful. Space agencies communicate through published ephemerides and orbital elements, not press releases. Absence of public commentary does not imply suppression. It implies data collection is ongoing. Mars provided the best observational opportunity. 3I Atlas passed within 29 million kilometers of Mars on October 3rd, 2025, at 0400 UTC. ESA's Mars Express and ExoMars Trace Gas Orbiter turned their instruments toward the comet. The high-resolution stereo camera on Mars Express and the color and stereo surface imaging system on the Trace Gas Orbiter captured images. The orbiter's CASIS instrument photographed 3I Atlas as a slightly fuzzy white dot amid streaked background stars. The distance was 30 million kilometers. The cameras are designed for imaging the Martian surface at ranges of hundreds to thousands of kilometers. Imaging a faint object at 10,000 times that distance pushed the sensors beyond operational limits. No high-resolution morphology was resolved. Spectrometers including NOMAD on Trace Gas Orbiter, Omega, and SpyCam on Mars Express attempted to measure reflected sunlight. Signal levels were insufficient for full spectral characterization. The observations confirmed presence, rough position, and brightness. They did not reveal internal structure. Mars orbiters are not equipped for deep space observation. The geometry was optimal. The instruments were marginal. The results were inconclusive. There has been no media blackout. There has been an observational blackout. 3I Atlas reached solar conjunction on October 21st, positioned directly opposite the Sun from Earth. No ground-based telescope can observe an object behind the solar disk. The glare saturates detectors. Coronal emission overwhelms faint reflected light. Space-based solar observatories like SOHO and STEREO can detect bright comets in their coronagraphs, but 3 Atlas passed 1.35 astronomical units from the Sun, well beyond the coronagraph field of view. From October 15th through November 10th, Earth-based observation was impossible. Perihelion occurred on October 29 at 11:36 UTC, 8 days after conjunction, during the blackout window. Whatever physical or chemical changes occurred at closest solar approach happened without direct Earth-based monitoring. November 11th is the reacquisition date. 3I Atlas will emerge into the morning sky for observers in the eastern pre-dawn. Magnitude is predicted near 11, requiring 8-inch or larger telescopes under dark skies. The object will be moving rapidly through Virgo, 1 degree per day, complicating tracking. Brightness may deviate from predictions. Comets are intrinsically variable. Outburst events, fragmentation, or deactivation can alter magnitude by several factors in days. The December timeline is critical. Closest approach to Earth occurs December 19th at 1.8. 3 astronomical units, 168 million kilometers. Not a close encounter by any standard, but the optimal geometry for spectroscopy and imaging from ground and space-based platforms. ESA's Jupiter Icy Moons Explorer, JUICE, will observe 3I Atlas in November during its transit toward Jupiter. NASA's Juno spacecraft at Jupiter is positioned for observations in late November and December. Data downlink from JUICE is delayed until February 2026 due to spacecraft antenna configuration and solar geometry. Juno operates on a limited telemetry budget. Observations are scheduled. Data return timelines are uncertain. Consider 3 interpretive frameworks. Scenario 1. Natural comet with unusual but not impossible properties. High carbon dioxide content explains early activity and extreme sublimation ratio. Alignment with ecliptic is rare but not prohibited, possibly indicating formation in a thin disk around a young star similar to our own. Large mass reflects selection bias. Bigger objects are brighter and easier to detect, implying a reservoir of smaller, undetected interstellar visitors. Sunward jet is geometric artifact, or localized outgassing, from a slowly rotating body. Arrival timing and trajectory are coincidental. This interpretation requires no revision of physics. It requires accepting a confluence of low probability events. Scenario 2. Disrupted object or fragment of larger body. 3. I-Atlas could be a remnant from a collision or tidal disruption event in its home system or during passage near another star. Fragmentation would explain the high mass, unusual geometry, and lack of rotation if the object is a tumbling shard. Localized outgassing from exposed volatile rich layers could produce asymmetric jet. The chemistry could reflect differentiated interior material not representative of primordial composition. This scenario explains some anomalies but struggles with the trajectory alignment and arrival timing. Fragmentation events randomize velocities and orientations. A fragment arriving on a near ecliptic trajectory is no more likely than an intact object. Scenario 3. Artificial or technologically augmented object. A probe or vessel capable of minor trajectory corrections could adjust its path to align with the ecliptic, facilitating observation of planetary systems concentrated in that plane. A propulsion system exploiting solar thermal energy or solar electric power could perform an O-berth maneuver at perihelion, using solar proximity to maximize efficiency of velocity change. Outgassing or exhaust plumes could mimic cometary activity while serving propulsive or thermal management functions. Timing arrival to coincide with Earth-based solar conjunction provides operational security during critical maneuvers. This scenario fits all observations, but invokes technology. It violates Occam's razor. It demands evidence of intent, which we do not possess. The Loeb scale, a heuristic framework for quantifying technological likelihood, assigns 3I Atlas a score of 4 out of 10, indicating increasingly abnormal characteristics deserving attention. The scale is subjective, non-peer-reviewed, a conversation starter rather than a validated metric, but it formalizes the intuition that something here does not fit the pattern. We have 3 interstellar objects in the catalogue. One resembled an asteroid, possibly metallic, with extreme elongation and anomalous acceleration. One resembled a typical comet, unremarkable except for its origin. One resembles a comet, but exhibits multiple deviations from expected behavior. The sample size is 3, Drawing conclusions from 3 data points is premature, but 1 out of 3 is 33%. And if 1/3 of interstellar visitors show anomalous properties, we need better models or broader explanations. The improbability stack is not proof. It is a call for scrutiny. Science proceeds by ruling out hypotheses. We rule out the artificial hypothesis, not by ignoring it, but by testing predictions. If 3I Atlas is a natural comet, post-perihelion observations should show typical outgassing, possible fragmentation due to thermal stress, conventional tail morphology, and trajectory consistent with gravitational perturbations only. If the object is technological, we might observe resumption of sunward jets inconsistent with solar heating geometry, deployment of smaller objects, trajectory changes exceeding predicted non-gravitational acceleration from outgassing, or structured emissions in radio, infrared, or optical bands. We watch, we measure, we compare to models. This is not speculation, it is hypothesis testing. November and December provide the observation window. The Hubble Space Telescope is scheduled to perform ultraviolet spectroscopy in November, measuring sulfur to oxygen ratios and gas composition. James Webb will reobserve in December after perihelion, comparing pre- and post-perihelion chemistry and morphology. Ground-based networks, including the Las Cumbres Observatory and the Zwicky Transient Facility, will track position and brightness. Amateur astronomers with apertures above 8 inches can contribute photometry and astrometry through the Comet observation database. The object will be faint, fast-moving, and challenging to locate, but it will be accessible. If fragmentation occurred, daughter fragments will separate along predictable trajectories, becoming individually resolvable over weeks. If outgassing resumes, spectroscopy will identify active species and map their spatial distribution. If the object has broken apart or deactivated, brightness will fade below detection thresholds. If none of those occur, if 3I Atlas emerges from perihelion intact, chemically stable, and on a trajectory indistinguishable from predictions, the anomalies reduce to statistical flukes and selection effects. But if something else happens, if the trajectory deviates by amounts inconsistent with sublimation-induced forces, if new jets appear in orientations that violate thermal models, if brightness changes suggest surface or geometric alterations, if spectroscopy reveals emissions inconsistent with passive heating, then we have a dataset that demands explanation outside the standard cometary framework. At that point, we do not conclude alien probe. We conclude unknown mechanism requiring new physics or chemistry. We publish observations. We refine models. We remain skeptical because skepticism is not cynicism. Skepticism is the discipline of proportioning belief to evidence, and evidence is what we will have in 60 days. The timeline is precise. November 11th, reacquisition in morning sky, initial post-perihelion photometry and astrometry. November 15th through 30th, Hubble ultraviolet spectroscopy campaign, sulfur-oxygen ratios, gas emissions. November 20th through December 10th, JUICE observations from Jupiter vicinity, infrared and particle measurements, data recorded for later downlink. December 1st through 31st, James Webb near-infrared spectrograph observations, carbon dioxide and water bands, thermal emission, morphology changes. December 19th, closest Earth approach, optimal geometry for high-resolution imaging and spectroscopy from ground and space assets. January through March 2026, 3I Atlas passes Jupiter at 0.31 astronomical units, potential gravitational perturbations, trajectory refinement, possible Juno close-range observations. February 2026, JUICE data downlink begins. Delayed results from November observations. March through April, final observability from Earth before object exits inner solar system. Terminal tracking by Southern Hemisphere observatories. Every date is a checkpoint. Every observation is a test. We are not waiting for aliens. We are collecting data to constrain models. If 3i Atlas behaves like a comet, it is a comet. If it does not, we expand the definition of comet or invoke new categories. The history of astronomy is a history of updating definitions when observations exceeded predictions. Oumuamua forced recognition that interstellar asteroids exist. Borisov confirmed interstellar comets exist. 3i Atlas, regardless of its nature, is forcing recalibration of what interstellar objects can look like and how they behave. That recalibration is scientific progress, even if the answer is mundane. So where does that leave us? An object with 8 documented anomalies has just passed the Sun during a month-long observational blackout. Reacquisition begins in 2 weeks. Comprehensive multi-wavelength monitoring will continue through March. Data from Mars, Jupiter, Earth, and space telescopes will converge over the next 6 months. Hypotheses will be tested. Models will be refined. We will learn something. The question is, what? If you want to stay on the timeline as this unfolds, tracking each observational window and data release as 3i Atlas moves through its final months in the inner solar system, subscribe now. The next critical checkpoint is November 11th, when ground-based observatories reacquire the object and the first post-perihelion data become available. The story is not over. It is entering the evidence collection phase. What comes next depends on what the object does, not what we expect it to do. Leave a comment. Are we watching first contact or sophisticated pattern seeking? Is 3i Atlas a 5-kilometer ball of dirty ice with unusual but explainable properties? Or are we seeing something that does not fit the taxonomy? The data will decide. But opinions now, before the November observations, establish baseline priors. When the results arrive, we will know whether our intuitions were calibrated or whether the universe surprised us again. November 11th. Mark it. The reality is this: we live in a galaxy with 400 billion stars. Planetary systems are common. Stellar ejecta from collisions, tidal disruptions, and dynamical scattering populate interstellar space with debris. The number density of interstellar objects in our local neighborhood is estimated at 0.1 per cubic astronomical unit. At any given moment, multiple interstellar visitors are passing through the solar system. We detect the brightest, the closest, the ones whose trajectories intersect our observational networks. 3i Atlas was discovered because it activated far from the Sun and grew bright enough to trigger automated detection algorithms. How many similar objects passed undetected because they were inert, dark, or missed by survey cadence? We do not know. We extrapolate from the detection rates and conclude that interstellar visitors are common. Approximately one object larger than 100 meters crosses inside Earth's orbit per year. Most are never seen. If interstellar objects are common, anomalous interstellar objects might also be common. Perhaps 1 in 10 exhibits properties outside the expected distribution. If so, we should expect to catalogue strange objects as surveys improve. The Vera Rubin Observatory will detect approximately 1 interstellar visitor per month once fully operational. LSST will find hundreds over its operational lifetime. The sample size will grow. Statistical distributions will emerge. We will determine whether 3i Atlas is an outlier or part of a population we have not yet characterized. That determination requires more data. More data requires time. Time requires patience. Patience requires trusting the process. But here is the uncomfortable truth. The process assumes naturalness. Our models are tuned to natural phenomena. We fit observations to physics we understand. When observations do not fit, we extend the physics incrementally, adding parameters, proposing new mechanisms, expanding boundary conditions. This approach has worked for centuries. It assumes the universe operates without intent. Rocks do not aim, comets do not navigate, ice does not compute. These assumptions are correct for every object we have studied in detail: thousands of comets, hundreds of thousands of asteroids, every planet, moon, and ring system in the solar system. Naturalness is the null hypothesis. It has never been falsified. But null hypotheses can be rejected. If we observe an object performing maneuvers inconsistent with natural forces, emitting structured signals, deploying subsystems, or exhibiting behavior correlated with external stimuli, the null hypothesis fails. At that point, we invoke technology, not because we want to, but because the data compel it. We have not reached that point with 3i Atlas. We are not close to that point. But we are closer than we were with Oumuamua or Borisov. And that proximity is why attention remains focused, why monitoring continues, why the observation campaigns are so comprehensive. Are we alone? That question has driven exploration for generations. We build telescopes to search for biosignatures in exoplanet atmospheres. We transmit radio messages toward nearby stars. We scan the sky for technosignatures, narrowband emissions, optical pulses, infrared waste heat. We find nothing. The silence is profound. The absence of evidence accumulates. Fermi's paradox deepens. Where is everybody? Maybe they are here. Maybe interstellar visitors are not always natural. Maybe some fraction of objects entering the solar system originated from technological civilizations, probes dispatched across the galaxy to study, sample, or signal. Maybe 3i Atlas is one of those probes. Or maybe it is just a comet. The only way to know is to watch. We have 60 days to reacquisition, 90 days to James Webb observations, 120 days to closest Earth approach. That is the countdown. When it ends, we will have data. The data will inform models. The models will generate predictions. The predictions will be tested against future observations. This is how science works. It is slow. It is methodical. It is self-correcting. It does not give immediate answers. It gives better questions. The question now is not what 3i Atlas is. The question is what 3i Atlas will do. Will it fragment like a natural comet under thermal stress? Will it fade as volatiles exhaust? Will it continue on a purely gravitational trajectory, perturbed only by solar and planetary masses? Or will something else happen? We watch, we wait, we measure. November 11th. Right now, 3i Atlas is behind the sun, hidden, unobservable, executing whatever physics or process occurs at perihelion. In 2 weeks it emerges. We point every available instrument at it. We collect photons. We analyze spectra. We track position. We compare to predictions. And we find out whether the anomalies were noise or signal. If they were noise, we move on. We catalogue 3i Atlas as an unusual comet and refine our models to accommodate objects like it. We wait for the next interstellar visitor and hope it is more typical. If they were signal, everything changes. Not because aliens, because the universe showed us something we did not expect, something outside the standard model of cometary behavior, something requiring new explanations. New explanations drive new questions drive new observations drive discovery. That is the cycle. That is how we learn. And maybe, just maybe, one of those new explanations involves recognition that we're not alone, that some of the objects moving through the void are not debris but envoys, not ejecta but artifacts, not chance but contact. Or maybe not. Maybe 3i Atlas is just a comet, weird but natural, and the real discovery is that interstellar space produces more diversity than our models anticipated. Either way, we learn. Either way, the universe surprises us. Either way, the question remains. Are we alone? November 11th, we get closer to an answer. Watch the sky.